Okay, we are starting the next chapter, that is work, power, energy. First we will make a quick revision and then we will go for questions and numericals, application of the same. So the first thing is, what is meant by work done? Work is always done. Now, when the work is done, when we apply force on a body and the body actually moves, displaced. If either force is absent or the displacement is absent, the work is not done. Right? If I am pushing a wall and the wall is not displaced, then I have not done any work. If I am not applying force and a body is moving by itself, then also I am not doing a work. Now, there are two quantities in it, force and displacement. Now this work, does it have any direction? Answer, no, it does not have any direction. It is only a quantity. It is only a size, and such quantities are known as scalar quantities, which has only and only size, that is, it has only magnitude, no direction. Okay. Now, if force F is applied on a body and it moves, we see it here. Here is a body, here is a floor. We apply force in this direction and there is a displacement of it in this particular direction, displacement, or we can say S. Then force is done, displacement is done, work is done. How to calculate it? Because there are two quantities, more is the force, more is the work done. More is the displacement, more is the work done. So work is proportionate to force, work is proportionate to displacement. So work is proportionate to F multiplied by displacement. We make it equal, work is equal to KFS. How can we eliminate K? Do you know the art of eliminating? You never had this thing. You always had work is equal to force into displacement. No, it is like this. Now, how to make K is equal to 1? Okay, I ask you the other way. When we apply force on a body and we increase the mass, then more is the mass, more is the force. So that was F proportionate to. If we want to accelerate a body, more is the acceleration we want to give, more is the force applied. So force is proportionate to. So force is proportionate to. Force is equal to. How you make this K as 1? Independent of? K is independent of medium. But why it is 1? This is anybody? Force is constant. No, if M is increasing, force is increasing. It's not constant. If more acceleration is required, we need to give more force. It's not constant. K is constant, but how K will have the value of 1 so that you have force is equal to mass into acceleration. Everybody do it because teacher is doing it. Right? Anyway, I wonder, and I have seen, no teacher is teaching this, that why this K has become 1. Pardon? Yes, speak.
Applying force will be equal to the product of mass and acceleration.
No, please speak again. I could not understand.
Without any without any opposing force, mass and acceleration will be equal to the
Without any opposing force. You mean to say F is equal to 0 in that case?
opposing force.
Opposing force is a force. Yes.
It will be 0.
It will be 0. Okay.
Then the applied force will be equal to the
KMA. Applied force F is equal to KMA.
it will be equal to MA.
Why? F is proportionate to M, F is proportionate to A, then F is proportionate to M into A. To make this proportionate equal, we have put this K as 1. Why? Dimension of force.
Mass into acceleration will be equal to the dimension of force. So in 3D system, K will be 1. Without any dimension.
No, I could not understand it. You see, the force between two masses is equal to F is equal to M1 M2 upon R square multiplied by G is not equal to 1. Is G equal to 1? We agree, G is not equal to 1. Here your teacher say K is equal to 1. You agree? Yes, K is equal to 1. Why? Okay. Anyway, this thing will come sometimes again and again. Because if you go for F is equal to MA, that is fine because we are doing it. But in physics or in mathematics, especially in physics, how we make the constant as 1. Please understand it. This is a basic thing. It will not be asked in NEET, I tell you. So it is a waste of time. You want to learn it? Yes. Okay. We have defined M. What is mass? We have defined acceleration. What is acceleration? For the first time in the laws of motion, we are introduced to force. Till that time, we don't know what the force was. We define that force is something which can change the condition of motion. Then we defined by the second law, the force is proportionate to rate of change of momentum, and we have come to this. The momentum was mass into velocity, and the change of velocity is equal to acceleration. But the law says proportionate, proportionate, proportionate. Till this time, we have not defined force. Defined the unit of force was not defined. Now, when we come here, I define force for the first time in physics. And how do we define it? I say, if I take 1 kg of mass and give it a push, such a strong push that it has an acceleration of 1 meter per second square. How much?
1 meter per second.
Then that force which I am applying, I will call that 1 unit of force, 1 Newton. That is the definition I made at this point. Not before, not after. Okay, I made it. So when I write this definition, how much mass I have taken? How much acceleration? And that force, how much I am calling? How much is the value of K? That is why K is 1. Because I defined force at this stage for the very first time. Force. So that becomes the definition of force. What becomes the definition of force? It is the quantity of force required to push an object of 1 kilogram to give it an acceleration of 1 meter per second square. That force required will be known as 1 Newton. Then this K will become 1. And after that we write F is equal to MA. Done. Now we have defined force. Now what happens? There are two masses of 1 kg put at a distance of 1 meter. They apply a force between them. How much force? We measure that force. But we already know how much is 1 Newton force. And we measure that force, that it comes to 6 point this into 10 to the power. What is the value of capital G? Whatever it is. That much force is applied according to our previous definition. And that is not 1. Because that is not 1, we have to write G. There we cannot write 1. Is it slightly clear? Yes. So, idea is, whenever for the first time we are introducing a physical quantity, we have to make a definition. We have liberty. We have liberty to create everything 1, 1, 1 and to make the constant 1. Understand? See, other example. Work is equal to KFS. Apply the force of 1 Newton. Do the displacement 1 meter. We have to do some work. And now we define this work as to be 1 joule. So this will be what? So what is our formula now? Work is equal to, yes, this K is removed. Now after that we cannot change that 1 joule. That is defined. After that, whenever we have to do the work, if we have 2 charges at 1 meter and push them, pull them, some work is done. There we cannot make K is equal to 1. We have to find the work by something, and that constant will be different. Because any quantity is defined once when we initially introduce it. And only at that time we have liberty to make K is equal to 1. In the physics, when you start from class 11, you go on defining quantity one after the other after the other. Everywhere you have a chance to make K is equal to 1, and we do it. Right? And this is a property of physics. Okay. So, let's come to this thing, that K is, this work is equal to force into displacement. Now in this, more of the job was done practically. How it was done practically? That if I have one object here, I am pushing in this direction, it is getting displaced in this direction, I have to do certain work, I am losing my energy. But if that body is not going in this direction, then I am not doing the work. That means force and displacement should be in the same direction. Then only work is done. Right? So we remember it as a rule. The force and displacement in the same direction. Now we have a habit to make the things complicated. What do we say? There is a roller on the road. I am applying force in this direction here, but it is going in this direction. This is displacement and this is force. Would you like to multiply the two? Yes and no. Okay, no, because these are not in the same direction. But why a roller should move unless there is a force? So there is a force, definitely, and there is a displacement, and I am supposed to count it. But so far now we have developed the knowledge of components or resolution. This force has components in this direction as well as in this direction that we have studied in 2-dimension knowledge. So this you very much know, how much is the component acting in this direction. And this is now we say that from the initial example we made a rule that force and displacement are always in the same direction. If these two are in the same direction, then which component of the force is responsible for this displacement? Right. So we decided S has to be multiplied with F cos theta. That will give us the work. So F into cos theta into S. Where? What is F cos theta? The component of force in the direction of S. And we have seen that work or energy, that is a scalar quantity. It has only size, it has only collection, only say magnitude, but it has no direction. So we decided that this type of multiplication which give us work like scalar quantities, we will call this multiplication as scalar. So why the name scalar multiplication of vectors? Because of this example. It is not that it is a scalar multiplication, therefore work is scalar. No. Because work is scalar, this multiplication is called scalar. Understand? So first we discovered this, and then we gave the name that this multiplication henceforth will be known as scalar multiplication. And in scalar multiplication, who is multiplied? F cos theta. And in the language of vector, this component is known as fx. This is fy. So fx multiplied by vector s gives, yes, what the, now these two should be in the same direction. For that we made another thing, and we will write it this type of product. This is indication of what? Please take that component which is in the same direction. It is indicator of that. Which component is to be taken? Cos theta, right? So we call it dot product. So work is equal to F dot S. The magnitude is Fs cos theta. Both are in the same direction. And this we do graphically by taking component in the same direction, right? This is calculation of work done. And according to this calculation, we can categorize the work done may be positive, negative, or zero. When it is positive, when the angle is less than 90 degree, because all cos theta less than 90 are positive, right? When it become negative, after 90 to 180, all these are negative, 90 to 270. So when it is an obtuse angle, then the work done is negative, okay? Or when it is in opposite direction, force and displacement, then that is in negative. Remember the best example of negative work done, that is done by friction. Okay? Now another thing, who is doing the work? Answer, we say, we use the words, the force is doing the work. Who is doing the work? Force. Yes, please remember. Another thing, agency who is applying that force, that agency is also given credit. He is doing the work. Both are correct. Like the work done by gravity, that is gravitational force, correct sentence, right? The work done by the pulley, that is also correct, because pulley is the one who is applying force. So we can use both of this, and technically both are correct. So work is done by force or agency which is applying the force. Okay. Now other thing, at any point can there be two agencies doing work on a body simultaneously? Simultaneously, both are doing work on one body, two forces. Is it possible or it's not possible? Possible? Give example. Two forces acting on a single body and both are doing work on that. Okay, then one force is gravitation. Other? No, your way of thinking is correct. Think a little more. Which is mechanical force? What is happening, you tell me? Where is the work done? What is the work done? Yes, he is very correct. I want to give the same example, this, and I am putting it up. There is a displacement, correct? This displacement is because of a force, correct? I am applying the force, I am doing the work. At the same time, Earth is applying force on it, mg. Against that force, mg is applicable, mg is applicable, mg is applicable, displacement is happening, mg is applicable continuously. So Earth is also doing a work on it. Earth is doing a work, I am also doing a work. And remember one thing, all the times, any work we are doing, there are always two forces acting on it, not a single force. Not possible. Right? We always ignore one force and we use that force which is acting. On the car, my engine is working, it is pulling the car in forward direction. I say, hey, my engine is doing the work, nobody else. Okay? Friction, remove the friction, I cannot stop the car. So friction is always working on it in backward direction. So friction is in this direction, there is a displacement here. So friction is also working on it. At any given instant, any body, if work is being done, it is always being done by two forces. We calculate for one, whatever we need to. So please remember this. Now, sign of the work done. If the force and displacement are in the same direction, the multiplication will be positive mathematically. But if they are in the same direction, we say the work done is positive. If they are in opposite direction, the work done is negative. And we know the friction is always opposite to the motion. So the friction is always doing a negative work. Always. Because if I am moving here, the friction is in this direction. But if I go on this direction, the friction will become in this direction. So friction is always doing a negative work. So this is negative. Then if we apply a force in one direction and the direction of motion is perpendicular to it, then it will be, yes, 0, because cos 90 is equal to 0. And what are the examples for it? Pardon? Coolie. Hey, you are insulting coolie. That coolie is not doing any work and we are paying him. You see, electron is moving around a proton. This is the force of attraction and this is the displacement. Earth is moving around sun. This is the force of gravitation and this is the displacement. The work done is 0. That is why work done is 0, no energy is lost. So Earth is moving around this from million of years because no energy is lost. Right? That is. Now for coolie. Is the coolie doing any work? What do you say? Here on the head of the coolie there is load which is acting in this direction and the motion of the coolie is in this direction. How much is the angle? Okay. Now, how the coolie moves forward? Why he does not move downward? How he moves forward? The answer is he pushes his foot back and moves forward. Why his foot doesn't slip? Because of which friction? How can we recognize that a body has energy? The answer is it should have mass and it should have velocity. Then it is having energy. How can we say that? How can we think? We think because that particular body has been put to motion because somebody did work on it. Otherwise, it should have been initially at rest. A body from rest to motion, how it comes to that? Somebody has done work on it by pushing it. So somebody has done work on it, that is why it has come into motion, and that is why it has capacity to do the work. The same work what was done on it. Now because it is in the condition of motion, we say the energy it contains is kinetic energy. Why we say it is kinetic? Because it is in the condition of motion. Please remember, the basis of energy is a loan. It is borrowed. Nothing in this world has its own energy. It is always borrowed. It is always given on loan. We have to borrow it, we have to return it. If we don't borrow it, we can't spend it. Like money. If you want to spend money, you should have money. But you can't generate money. You have to borrow it from someone. Either from our parents we do it, or we do some work and our employer, he gives us the money. But we don't produce money. The same thing is for energy. We don't produce energy. That is law of conservation. And it has to be borrowed from someone. So somebody has given energy, and now I have a capacity to do. How it is recognized that something is moving, somebody has done work on it, we say sure it has got energy because it is in motion. What is the proof? The proof is, if this body is moving like this, I put a stationary object here, when it goes and hit it, this starts moving. A force is applied and there is a displacement. That means it has a capacity to do the work. So it has energy. And why it was so? It is standing like this. Now I touch the two, it does not move. When it is in motion, then only it can push, apply the force, and it can move. That means only object which is in motion has got energy. Okay. This is kinetic energy. Another type of energy, capacity to do the work, is potential energy. Potential is location, position, configuration. That all makes potential energy. If the position of a body is such that it is able to do the work, how do I know? I have to try it. If I leave this body, it will fall down. When it falls down, I put a fan here, or you can say a small toy which is like a truck or a fan. It falls down on it and it moves. There is a force, there is a displacement. Work is done. Who has done this? Now I keep it here and leave it, it doesn't move. I keep it here and leave it, now it moves. That means the energy is due to position. This energy which is due to position is known as potential energy. What is the source of potential energy? It has borrowed it. What is the source of kinetic energy? It has borrowed it. That is same. Only thing, after borrowing the energy, somebody is doing the work on us. We store it either in our motion or in our position. Like a water is stored on the overhead tank. It has energy. You open it, it will come down and do rotation of anything, turbine or something. That means it has a capacity to do the work. It is not in motion, but it has a capacity to do the work. So that is because of its position. It is there, we call it potential energy. And if something is moving, that also we have explained, that is also capacity to do the work, and that is known as kinetic energy. And both are generated because somebody has done work on it and that work has been stored on it. Now, this can apply force. One thing we should remember in this process, lest I forget, I tell you just now, how potential energy is doing the work. Please remember, the potential energy first converts to kinetic energy and then it does the work. Like if I want to move a turbine or a fan, toy fan which is on the floor, what I need? I need to apply the force and do the displacement. There is a water on the tank above. If I touch it with the water, it will not move. I open the water from their tap, that water comes here. Its potential energy converts into speed. Because of the speed, it has now kinetic energy and it touches it. The moment it touches, that energy is doing work on this. It is converted into work done. So what was the steps? Potential energy, kinetic energy, work done. Right? So it is just to remember. Now, this kinetic energy and potential energy, how can we calculate it? The answer is somebody has done work on it. That is why they store it. So let's calculate the work and do a formula in which velocity will appear of the body. So, and that is very easy to do it. You have been doing it. Where is the duster? Oh, let's see. Here is a body at rest. I use my energy, muscular energy, apply the force F on it and keep pushing up to a displacement of S. That means I am giving it acceleration. When I am applying force, what I am doing? Giving it acceleration. Its velocity was initial velocity. Suppose it was 0. I have started force and push it. I spend my energy and doing work on it. Now it goes to S distance. How much work I have done? Yes, tell me. Fs. This is the work I have done on it. Now it has reached here. My work is lost. I lost my energy. I have given work to it. Because of that work, it has attained certain velocity. Because when we apply force, we are doing acceleration. We are passing through a certain distance as it has gained certain velocity. How much V is that? Plus 2. What is that? AS. Okay. Now, V square. This was 0, so this is equal to 2AS. Right? Now, work done is force into this. 2AS. Multiply with mass on both sides. So this will become correct? Keep this 2 here. What this will be? Is equal to M into A into S. What is M into A? F. S. What is Fs is equal to? Work done. So, the work done Fs has another formula what? Why we should convert it to this? Because here, what we recognize, a car is moving with a velocity of 40 km per hour. What is the data available with us? Velocities. What is the data available with us? Mass of the car. These two data available. Somebody has applied a force F given by the distance S, we don't know, for the car. For the car, what is data with us? Velocity and mass. Therefore, we want a formula which is in velocity and mass. But we should not change the meaning. Half mv square, do not change the meaning. But the data required is m into v square. So this becomes the formula for kinetic energy, because it is using the terms used for kinematics, V. Understand? So this is the format of kinetic energy. Now potential energy, again F into S. F, if I am lifting something against gravity G, then how much is the F? Mass into acceleration, mg. I take it to the height h. How much work is done? mgh. So work done is equal to mgh. This is the change in energy of that body, because that is the work done on it. So work done on a body, that is giving storage to a body, can be expressed either in the kinematic terms or in the static term, height. If we convert it into this, we give it a name, kinetic energy. If we convert it into this format, we give it a name, potential. Both are same. Both are same. Somebody has done work on it. So this is what is data given to us according to this. And now you can understand it one thing very well. This can be converted to this, and this can be converted to this, right? So conversion is possible. So this you should remember, this conversion. Now the most important thing in the work, that is work energy theorem. Work energy theorem. Please try to understand it. Whenever we do work on a body, I lose my energy and that body gain energy, right? This is transfer of energy, one thing. Now if a body has got energy 100 joule, that body is applying force on something, doing displacement, doing the work, and it is doing the work, it has done 40 joule of work. What do you expect? It is still having 100 joule of energy? No. It is very simple mathematics. We simply say you have 100 rupees, 40 you have spent, 60 is with you. That 40 you have spent is the work done, and 100 minus 40, 60 is the, 100 minus 60, 40, that is the work done. 160 are your energies. What are those energies? Energy before doing the work, energy after doing the work. So I make a very simple statement. If you make a difference of the two energies, before and after, then the difference of energy is equal to work done. This is work energy theorem. So simple. So what is work energy theorem? That work done by any body is equal to the difference of energies before doing the work and after doing the work. Very simple, right? So that gives us a method of calculation of the work done, and this is a basis which explains, if you have no money in the purse, you cannot spend. You have no credit card. Okay? So that means if you have no energy, you cannot do the work. This is important. If we are doing work on something that will not go waste, its energy has to increase. If something is doing work, its energy is definitely decreasing. That is work energy theorem. So please remember these principles. These are the principles with which you solve many problems, many applications. You see an application, there is no change in the energy. What is our conclusion? It has not done any work. So when they say calculate the work, we say what work? He has not done any energy. No loss of energy, no work is done. So we can find solution. If you know all the principles, you never know what will click, and you will find the solution with that. Right? So no work can be done without losing energy. Nowadays you will see many articles, WhatsApp articles here and there. People are inventing machines which are working without petrol, because petrol gives energy. So please remember, no machine can work without without using energy. It's not possible. People say, yes, I will invent that. You cannot. And if you do, you are God. Yes, because only He can do it. Anyway, this is work energy theorem, and you can very well prove it, but because there are no theoretical questions in NEET, I need not to give you a proof. This is a proof for that. In case we have this here, what this will be? V square minus U square. And that will be what? V square minus U square is equal to 2AS. If I multiply this with M, divide with this 2 here, what this will become? What is this? Force into displacement, work. What is this? Energy. Kinetic energy afterward, kinetic energy before the doing work. So this is what? Change in energy. Change in energy is equal to work done. This is the proof of work energy theorem. So once we understood this, okay, so this is everything we had to do in this. Only one thing, so that we finish the theory part of it. A very famous example of kinetic and potential energy. We leave a ball from here. The sum of K and P at this point, at this point, at this point, all remain same. It may be either equal to mgh or equal to half mv square, wherever you do it, because you know the conversion that can be done. That is one thing. Other thing, what I wanted to tell you is, one thing which is left is work, power, energy. Power. What is power? Power is a very important thing, though it's a very small thing. Yes? Power, you should remember two formulas. Number one, work done by power. Whose power? Answer is the one who is doing the work. The agency which is doing the work. Oh, yes. So, the agency which is doing the work. In 1 second, whatever work can be done by that agency is known its power. If a machine has taken time T to do the work W, then in 1 second how much work it can do? W upon T. So this becomes the formula for power. Right? So power is equal to work upon T, and with this we get work is equal to power into time. Please remember, this is a very versatile formula, and we will use it all over the physics all the time. That energy is equal to power into time. What is the unit of power? Watt. What is the unit of power? Watt. How much is 1 watt equal to? If 1 joule work is done in 1 second by a machine, its power is 1 watt. That is 1 watt. So watt is joule second. In 1 second the work done is watt. So watt and joule are equal if the time is 1 second. Watt is joule. A 100 watt bulb is doing 100 joule work in 1 second. So we multiply it with time, and that will become watt into second. If you increase it kilowatt into hour, that becomes the unit of watt. Power or work? Please remember, kilowatt hour. Kilowatt multiplied by hour is a unit of, kilowatt into hour is a unit of work, that is energy. That is how we pay our electricity bill. Electricity bill, energy bill are given in the unit of kilowatt hour. Why? Kilowatt hour is a unit of energy. Right. So this is about power. Work done per second. Now for the power we have another formula. This is work. Work is equal to force into Displacement. Displacement upon time. Velocity. So we have another formula, that is what? Force into velocity. So this is very important formula where work and time is not possible. We have attached one engine with the train which is applying the force of 1000 Newton, and the train is moving with a speed of 72 km per hour. What is power of the engine? Multiply the two, you get it, right? The power of the engine is 12 kilowatt power, and the train is moving with a speed of 72. What you can find? Force applied. Is this clear? Okay. So this is all about this work, energy, power, and in this chapter, if the questions based on this, you can do it. Only one topic is left, that is, what is that? Collision. Yes. So we can do that collision in the next class, right? Please carry on.